Hi, welcome back to the second lecture of group theory. So let us recall what we have studied so far. So in the last lecture, means lecture 1, we have formally defined what's a group, and we said that is a non-empty set allowing the binary operation, and it is basically looks like a tuple like that, a set, comma binary operation, and we expect that to satisfy three properties. One is associativity, that is for you take any three elements g1, g2 and g3, and it doesn't hamper if I first do binary operate with g1 and g2 and then do that g3 with the product, and it will be same if we first do operate in between g2 and g3 and then operate g1 from the left side of the product. That is g1 star g2 star g3 is basically same as g1 star g2 star g3 here. So it is associativity. Means basically this position as brackets doesn't hamper if I just shift it one element to the right. Secondly is that the presence of an identity. That means for all small g belongs to capital G, I have a unique identity element which is basically denoted as E, such that G star E is basically E star G is same as small g. Okay, so it basically doesn't make any difference with whether I operate E from the right side or I operate E from the left side. The product will be basically small g itself. And the presence of inverse, that means for each small g in capital G, I have unique G inverse. So this identity element is unique for all the elements in G. But this inverse is basically specific to the choice of our element. So for whatever small g I'll be choosing, the G inverse is basically unique up to the choice of the element. So G star G inverse is basically same as G inverse G is your E. And also we said that some examples like the set of integers along with addition, set of real numbers along with addition, set of non-zero real numbers along with the multiplication, set of rationals along with addition, as well as set of non-zero rationals along with multiplication. Similarly, field of complex numbers means the group of complex numbers along with addition, and the multiplicative group of complex numbers all are basically groups. So these are basically trivial groups, but we also gave some example of some non-trivial groups as well. That is set of all group matrices of order n cross n. That is a group under the addition, and also the set of all group of n set of all matrix of n cross n with determinant non-zero. That is known as a general linear group. That is GL and R. So this is a group under the matrix multiplication. So all these are some infinite groups. Also there are some finite groups as well, which is basically a symmetric group of order n, which is basically the group of all bijective maps from n a set of n elements to set of n elements, and these of course are group under the composition. Secondly, we also discussed something called the Z modulo NZ, and this is a group under the modulo addition. How the modulo addition is defined. So Z modulo NZ is basically set of it is basically a collection of some sets which is basically denoted as 0 bar, 1 bar, 2 bar, sometimes n minus 1 bar. So 0 bar basically contains that all the elements which are congruent to 0 mod 2. That means all the elements that basically gives 0 as your remainder upon the division with n. That means the elements basically should be divisible by n. Similarly, 1 bar is basically all those integers that gives remainder 1 upon division with n. That means n divides z minus 1. So we can just write that to be z is congruent to 1 mod n. This we can write that to be z is congruent to 0 mod n. Okay, and also here you can write this to be similarly 2 bar is basically all the elements or all the integers that gives 2 as a remainder upon division with n. That means basically z is congruent to 2 mod n. And similarly up to z is congruent to n minus 1 mod n. Okay, so these are the sets of basically denoted as 0 bar, 1 bar, 2 bar. So it has another representation like just box bracket of 0, box bracket of 1, box bracket of n minus 1. Okay, so then z modulo nz is a group, and what is the modulo addition that we talked about? So the modulo addition is basically if we take any two elements a bar and b bar, so of course a and b has to be strictly less than n, right? So if their addition is basically n, then it is 0 bar. If their addition is larger than n, then a plus b minus of n. So that it will take the difference between a plus b and n, because if you divide a plus b with n, this particular one is going to be as a remainder, right? That is means if a plus b is larger than n, and if you divide a plus b with n, what is the remainder? The remainder should be a plus b minus n, right? So that means you have to take the set which is basically identified by a plus b minus n. Then you just take the bar of that, right? That's why you just take the bar. Similarly, if a plus b is itself less than n, so that means you cannot divide a plus b with n. So then a plus b bar will be your value of the addition. So this is what we define the modulo addition, and you can check that it is a group. Okay, now let us move furthermore that now okay, so also we define something called the abelian group. That means whenever I take any two arbitrary elements g1 and g2, so that the binary operation between g1 and g2 doesn't have any relation with the position of the element. That means g1 star g2 is same as g2 star g1, so it is independent to the position of the elements. So as an example, we defined m and r with respect to addition: z plus, r minus 0 dot, q plus, q minus 0 dot, etc. These are basic examples of abelian groups. Also, your z modulo nz, this is also abelian. So that means it is basically doesn't make any sense. So let's say we take a bar plus modulation is b bar. So it is basically, it gives you either it will be 0 bar if a plus b is larger than, if a plus b is same as your n. This is a plus b minus n bar if a plus b is larger than n, and thirdly is that it is only a plus b bar if a plus b is less than n. Okay, and if your a plus b, now what about we take b plus a b bar modulation to a bar? So that is basically, it will be first, it will be giving you if b, so it will be 0 bar if b plus a is equal to n. Now b plus a is basically addition under the z plus only. This addition is there. So that means in z plus is abelian, right? And a and b both are integers. So a plus b is basically same as b plus a, right? So a b plus a is equal to n if and only if a plus b is equal to n. Similarly, it is b plus a minus n bar if b plus a is larger than n. Now what is b plus a minus n bar? So b plus, we can write that to be as a plus b minus n itself. Okay, that is if, and basically this is in equivalent to that, and this condition is equivalent to a plus b is larger than n, and similarly it is itself b plus a bar if b plus a is less than n. Now b plus a bar is basically similar to a plus b, right? So if a plus b, and condition is basically getting overlapped with a plus b is less than n. So that means you say that these conditions are basically for a plus a bar modulo addition to b bar and b bar modulo addition to a bar, the conditions are basically getting overlapped with each other, right? So that means you can easily see that. So you see that here is the conditions, this condition and this condition, all are basically getting equivalent here actually. Okay, so that means we can write that a bar modulo addition to b bar is basically same as b bar modulo addition to a bar. So this is because z plus is abelian. This is a key idea. Okay, all right. Now we'll try to give a multiplicative structure on z modulo nz. Okay, so now if we want to show that z mod nz is a group, is also a group under the multiplication, so let's see what are the procedures that we can go on. First of all, we need to multiply two elements from z mod nz. So let we have a bar and b bar belongs to z modulo nz. Okay, so what we can do, we can just write a bar modulo addition to b bar is basically, so this must belongs to z modulo nz. Now we all know what's the construction for z modulo nz, means we all know how to construct these cosets. So these are basically based on the reminders of what we are getting after dividing with n. So that's why we just write that a bar mod b bar, this is to be as, first we multiply a and b together, then I take modulo n, means I will take the remainder of that, then I take the bar, the coset of that. Okay, so ab mod n bar. So if this is, so what is the multiplication? So this is how we define the multiplication of two elements in z mod nz. Now what are the properties? So first of all, associativity. So what is associativity property? So let us assume that we have taken 3 points, a bar, b bar and c bar belongs to z mod nz. Okay, so then what about a bar modulo addition b bar modulo addition c bar, so which is basically a bar modulo addition to bc mod n bar, right? So now now if I multiply this one, is basically I'll be getting mod of a b c mod n bar, and this is basic. Again, if we take a bar modulo addition b bar and modulo multiplication c bar, then it basically will be getting, yeah, it's modulo, it's not modulo addition, this is modulo multiplication. So this is modulo multiplication and this is modulo addition. So a bar dot b bar dot c bar is basically, is also same as ab mod n bar dot c bar. So again it is basically coming to be as bar of a b c mod n. So both are basically same. So a bar dot b bar dot c bar is basically same as a bar dot b bar, then with c bar. So both are same. So that's why modulo multiplication associativity is there. Secondly, what about the identity? So you can easily find that if you take 1 bar belongs to z modulo nz, sorry, and then you take any a bar from zn, so that means a bar dot modular multiplication to 1 bar is basically bar of a times 1 mod n. So it's basically same as a mod n bar, right? Now since we have chosen a bar from that element, so a must be same as, you can assume that a is less than small n, so it is basically same as your a bar. Okay, so this is true for any a bar belongs to z modulo nz. That's why it is identity element. But what about the inverse? So for inverse, let's assume that a1 belongs to z modulo nz. So then if we consider two, if you want to get some inverse of a1, that means I need some a2 bar belongs to zn such that a1 a2 bar is basically 1 bar, right? That means a1 a2 this must belongs to 1 bar. Okay, so that means basically we need that a1 a2 is congruent to 1 modulo n, so which means that n must divide a1 a2 minus 1. So that means we have a1 a2 minus 1 is basically sum nk1, which basically means that a1 times a2 plus n times minus k1 is basically 1. So that means 1 should be the linear combination of a and n, a1 and n, with respect to the integer coefficients. So that means this belongs to a1x plus ny such that x comma y, this belongs to integers. So that means a1 and n, this must be co-prime. Okay, because we know that there is a theorem that says that a and b are co-prime, means not co-prime. So if GCD of a and b, if GCD of a comma b is basically ax plus by. Okay, so that's why if a and b are co-prime, so you can just write that to be as 1 is basically ax plus by. Okay, so if ax if a and b are two integers and their linear combination is 1 with respect to integer coefficients, then it is both the elements has to be co-prime. So that means the multiplicative inverse will exist if and only if a1 and n are co-prime. Okay, so that means we need to choose, it is not possible to get multiplicative inverse for any arbitrary or for any non-zero elements from z mod nz. So that's why we need to shrink the set towards something called z modulo nz star. So it is basically the multiplicative set of z mod nz that basically is consisted of all I bars such that I belongs to 0 to n minus 1 such that I and n are co-prime. Okay, then each and every element in z mod nz star will have an multiplicative inverse. And of course, since all these three properties, that is associativity as well as the presence of identity, exist in for any case, for any for the overall Z mod nz, so that should of course exist for the Z mod nz. So in fact, identity is one bar, so 1 and n are co-prime, so one bar has to be there in Z mod nz star. Okay, so of course one bar is there because 1 and n are co-prime. So that's why Z mod nz star is a multiplicative subset of Z mod nz, and Z mod nz star, this will be a group under the multiplication. So it is, you can just write, it's a modulo multiplicative group. Okay, now what's the cardinality of Z mod nz star? Since Zn star is basically subset of Zn, and Zn is itself finite, so that means Zn star, it has to be finite. Now what is the cardinality of Zn star? So the cardinality of Zn star is basically the cardinality of all I belongs to 0 to n minus 1 intersection integers such that I and n are co-prime. So it is basically phi of n, where phi is Euler's phi function. Okay, so that is basically n times 1 product of p divides n 1 minus 1 over p, where p is basically the prime. Okay, for example, let us consider n to be your 8. So what is your Zn? It is 0, 1, 2, 3, 4, 5, 6 and 7. But what is your Z8 star? This will just be taking only 1, 3, 5 and 7. So 1, 3, 5 and 7. In fact, what is your phi of 8? So phi of 8 is basically 8 times 1 minus 1 over 2 is basically 4. That's why cardinality of Z8 star is basically phi of 8, which is basically 4. Okay, so we have got that Z mod nz star is a multiplicative group with respect to modular multiplication. Okay, now let us consider E and F are two groups. So E is associated with binary operation star and F is associated with binary operation hash. Okay, so now if it is a group, then we can consider a non-empty set to be E cross F, right? So you can define a binary operation E cross F over, a binary operation dot over E cross F such that for any two elements E1 comma F1 dot E2 comma F2, that we can get into. So E1 and E2 will be first multiplied via star, so E1 star E2, then F1 and F2 can be multiplied via hash, that is F1 hash F2. Okay, so then E cross F, this will be a group. So in fact you can check that E1 F1 dot E2 F2 dot E3 F3 is basically giving you E1 star E2 star E3 comma F1 hash F2 hash F3. This is basically same as E1 F1 dot E2 F2 dot E3 F3. Okay, so this is associativity. Secondly is that presence of identities versus identity. So I can choose. So since E and F both are grouped under different binary operations, so I can take the identity element of G and identity element of F then and make that a tuple. So this belongs to E cross F. Okay, this is identity. And thirdly is that presence of inverse. So if I take any element, let's say E1 comma F, let's say E comma F, from E cross F. So small e belongs to capital E, so this has an inverse, let's say E inverse, that belongs to E, and F belongs to capital F, so F will have F inverse that belongs to capital F. So that means we have that E inverse comma F inverse which belongs to E cross F, and then we have that E comma F dot E inverse comma F inverse is basically E of G comma E of F, because E star E inverse is giving you E of G and F star F inverse is giving you identity element of F. That's why it is EG comma EF. So that's thus we get that is associative property. Okay, all three properties are there. So associativity, presence of identity, and presence of inverse, all three properties are there. So we get that E comma F, E cross F with respect to dot is a group. Now let us consider what you can speak about the abelian property of that. So let's say we take E1 comma F1 and E2 comma F2, this belongs to E cross F. So then E1 comma F1 dot E2 comma F2, so it is basically E1 star E2 comma F1 hash F2, and on the other hand we have E2 comma F2 dot E1 comma F1, that should be E2 star E1 and F2 hash F1. Now if both has to be same, then each of them need to be same, that is this one should be same as this one, and this should be same as this one. Okay, that means your E and F both has to be abelian by independently. Okay, so then only you can say that E cross F is abelian. Okay, so just we need to define this one as something. So this particular group, which is E cross F, is basically said to be the direct product of E and F. So let us consider that E and F are two groups. So by the way, so all time I will not write E comma star or F comma hash. So whenever I'll be saying E and F are two groups, you have to understand that I'm just associating some binary operations with the group. Okay, every time I will not write in this form, but you have to understand by this one by default. Okay, so whenever we have E and F are two groups, then we have E cross F. This is said to be direct product. Okay. Okay. Now there are some lemmas. So the lemmas says that these are basically very basic lemmas that we have already considered. So first of all is that, let's say identity element in G is unique. Okay, that means let's assume that we have two identity elements E1 and E2 in G. So what about E1 star E2? So first you consider this is your first this one identity, and this was in general element, E2 to be in general element. So that has to be E2 star E1. This should be E2, right? Again, you consider E1 star E2 itself. So now you consider this is identity and this is your in general element. Okay, then it will be basically E2 star E1 again, and is E1. So that means E1 and E2 has to be same, right? So identity element is unique. Again, let us consider. So secondly is that inverse of every element is unique up to the choice. Okay, so let small g is capital G. It has two different inverse. One is G1, one is G2. That means G times G1 is basically same as G1 times G is basically E. And similarly we have G times G2 same as G2 times G is basically E. So note that I'm just excluding the binary operations here. Okay, so here also I will not every time write binary operation star in between the elements. I will just write G1 and G or G and H, whatever be that. You have to just understand by default, right? Okay, now what about your G1? So G1 is basically G1 times E, right? Like the identity. Okay, so that means you basically get it here that G1 times G times G2. Okay, now by associativity we get that G1 G times G2. Now G1 is basically identity. It is basically same as your G2. So G1 is same as G2. So inverse is basically unique for each small g up to choice of up to the choice of the element. Okay, secondly, let us consider that G1 and G2, these two elements in G, so then the inverse of their product is basically G2 inverse times G1 inverse. So is okay. Now as you have said that it is unique up to choice, so that means it is enough to prove that G1 G2 has inverse like that. G1 inverse, G2 times inverse times G1 inverse. So let's take G1 G2 times G2 inverse G1 inverse. So what I will be getting that G1 G2 G2 inverse then G1 inverse by associativity. Okay, in fact for multiple times you have to associate first. You have to just like G1 times, so first what you have to do that you have to take G1 and then combine these two, G2 times G2 inverse G1 inverse, then you have to multiply this one. So G1 times G2 G2 inverse, and then G1 inverse. Okay, so that is what you have written here very quickly, and this is basically G1 times identity times G1 inverse. So then we basically get that G1 inverse is identity. Okay, similarly, if we take G2 inverse, G1 inverse, G1 G2, so again we get that G2 inverse, G1 inverse G1 times G2 is basically G2 inverse E times G2, which is basically G2 inverse times G2 is E. Okay, so that means G1 G2 times G2 G1 G2 inverse G1 inverse, and G2 in G2 G1 inverse times G1 G2, both are is basically giving you identity. So G2 inverse G1 inverse, that basically acts like a inverse of G1 and G2, and since inverse of an element is unique, so by uniqueness of the inverse we get that G1 G2 inverse is basically G2 inverse G1 inverse. Okay, and another very basic lemma is that A inverse whole inverse means first we take any element small a from the group G, and I take the inverse of that is A inverse, and I'll take the another inverse of that is A inverse whole inverse, which is basically same as your A. That is basically very easy, like A times A inverse times A inverse times A is basically identity, right? So now that means this particular one gives you that A inverse whole inverse is basically A. It's very basic by definition. Okay. Now there is something called another lemma. Let's say so what's lemma? So it is okay. So it is 4, and another lemma 5 is the cancellation law. What does the cancellation law says? That if we have G1 G2 same as G3 G2, so this will imply G1 is same as G3. Sorry. So this is cancellation from the right side, and also cancellation from the left side is there, like G2 times G1 is G2 times G3. This will also imply G1 is same as G3. So this cancellation from the left side is cancellation from the right side. Okay, so basically we get that. So it is very easy, like we multiply both sides with G2 inverse from, in this case, so G1 G2 times G2 inverse is G3, G2 times G2 inverse is basically G1 is same as G3. And again here we get for the second one, I multiply G2 inverse from the left side, and then we get that G2 inverse G2 G1 is same as G2 inverse G2 G3, basically same as your G1 is same as G3. Okay, so that's why for group operation cancellation law is there from both the sides. Okay, now there is a basic notation which is basically says that suppose we have G is a group. Okay, So if G is a group, then the cardinality of G is basically considered to be an order of G. Okay? And let small g belongs to capital G, then order of small g is basically the infimum of small n belongs to capital N, such that G times G times G times G, so on up to G, this up to n times, is basically your identity. So that means for every element in G, I'll be, if you want to consider the order of G, so that means if we need to I need to get at least some natural number, so that if I repeat the multiplication G with itself for that n times, that will be identity element. And whenever, if we get that order G has no such element, no such natural numbers, then we say that G is of infinite order. Okay? Alright. Now let us consider that G is a finite group. So basically there is a theorem, or is a proposition. The proposition says that let cardinality G is finite, is a finite group, then order of G divides the order of G. Okay? So let small g belongs to capital G be an element. Then we consider the order of G to be like infimum of small g belongs to capital G, such that small n is natural number, such that G times G, so on up to G, which is basically n times, this is your identity. Okay? Now if it is that, so then let us consider H to be the collection. For now just consider this to a subset of G. So a power m such that m belongs to an integer. Okay? Now let that order of G is n, right? That means a power n is your identity. Make sense? So if a power n is your identity, so then what we get, that order so then then basically get that let a power n plus 1, this is basically a power n times a, that means e times a, basically your a. What about a power n plus 2? It's basically a power n dot a square is basically e times a square is your a square. And thus what about your a power n plus n minus 1 is basically a power n times a power n minus 1. So it is basically a power n minus 1. Okay. Now let us consider that if we have, so that means we see that up to after n onwards, if we raise the power, then the elements basically are getting repeated, right? So that means basically we have that h is precisely of the form identity a square so on up to a power n minus 1. Okay. So then what we get here basically, now let that we have a power I is basically same as a power j for some I is not equal to j that belongs to 0 to n minus 1 intersection natural numbers, in integers. Okay, means we are taking okay, so let us take not 0 to n minus 1 for some I comma j belongs to 1 to n minus 1 intersection natural number. So then we basically get that a power I minus j is your 0 or identity, right? Now I is inside n minus 1 less than n and j is less or equals n minus 1 strictly less than n. So that means basically we have that I minus j, this has to be basically less or equals n minus 1 and this is strictly less than n. That means I minus j will be less than n. So a power I minus j is identity, but we have that since a power I minus j identity, so n has to be a least with this property, so n has to be strictly less or equals I minus j. Okay, so this is not possible always, so that means I and j, so it's not be possible. So this is 1, but this is 2, so 1 and 2 are contradicting to each other. So that means we have that I and j has to be same if ai and a power I and a power j has to be same. Okay, so that means what is the number of elements in H is basically n, right? It's basically order of G. Okay, now if it is the number of elements of H is basically order of G, so we have said that for now just consider this to be a subset. So for now consider this to be a subset, right? So now if we can show that cardinality of H divides the cardinality of G, so then we are done, right? Okay, so when it is possible that when cardinality of G of any subset, let's say G any subset, so this is our main question that we will be triggered out. So the question is that when let's say H is subset of G, cardinality of H will divide the cardinality of G. This is our question. Okay, so to trigger this question we need some property called subgroup. So in general it is not true always. It is not true always. So for that case we need something called more property on H, that is to be a subgroup. Okay, means in general is not true means whenever I take any subgroup, any subset, let's say H is any subset of G, it is not always true that cardinality of H1 will divide cardinality of G, even if G is finite. Yeah, because if it is not finite, then there is no point of talking about the divisibility of cardinality of G with respect to cardinality of H1. Okay, so what is a subgroup? So subgroup means let H is subset of G, of course G is a group, and H is subset of G, so then H is said to be a subgroup if H is group with respect to the restriction of the binary operation on G to its own right. So what basically this means? So basically I've said that two things. So binary operation with restriction of binary operation on G. So what is a binary operation? So binary operation means, suppose G is associated with binary operations dot. So dot is basically mapping from G cross G to G. Okay. Now if I restrict dot to H, so this restriction should be H cross H. I need that to be lie inside H again. Okay. So this is said to be restriction. So if H is a subset of G that has this fine property, and with respect to this multiplication, it is H with respect to H dot restricted H with a restriction binary operation. This is also a group, right? So that means that basically gives the local version of the group. Now the question may appear that what is identity? So let EH belongs to H, this be identity. Okay. Now let small h belongs to capital H be an element. So we have that EH times H, or H times EH, this is your H, right? And we also have that whenever H is subset of G, then H is also H dot E of G, the identity element of G, times EG of H is your H, right? For all G, right? Now you choose H to be your EH itself. Okay. So basically then you get that EH times E of G is basically E of G times E of H is basically E of H. Okay. If we just take H to be an EH again. Now we all know that in case of a group, the identity element is unique, right? That means by uniqueness of identity element, we have that EG must be same as your EH, right? In H. Okay. So the identity element of G has to be same with the identity, has to be there in the identity element of H. Means if we consider G is a group like that and H is subgroup like this, so identity element should be there in H. Okay. So then G is said to be a subgroup. So basically this is the main condition, that H should be a group with respect to the restricted binary operation. Okay. So as an example, let's say Z with respect to addition is a group. So it has a subgroup like for any natural number nz is also a subgroup of Z, right? Okay. So this is your subgroup, and alright, so let us stop it here, and maybe from the next time onwards we'll see more properties of subgroup. And the main question that triggered us to study the subgroup is that whether this divides G or not. So that is basically coming via something called Lagrange's theorem. So yeah, we'll see this thing by the next time onwards. Okay, so thank you very much.